1. All right, so ever been to McDonald's? Yes, we have been. You go to the drive-through window and you see a menu. And in that menu, you're going to, every item, by law now, every item has a caloric value. I don't know why. I mean, do you really think that if you weigh 400 pounds, that the fact that a Big Mac is 1,100 calories, you're going to sit there and go, oh, I can't eat. That's 1,100 calories. I don't know. Has anyone ever decided not to eat something because you saw how many calories it was? Anybody? Okay, some people. All right, good, good. What blew my mind the other night was when I was reading that a large sonic blast was a whopping 1,400 calories. Okay, a large sonic blast was, I believe they said it was 80 grams of carbohydrates. Okay, you need to understand, as got somebody who does keto, that's 3 days worth of carbohydrates for me in one dessert. So I didn't realize that. Question is, how do they know that? That's what this lecture is all about. That's what this lecture is all about. Question number 17. What do we call the part of chemistry concerned with the study of heat flow that occurs during chemical reactions? Okay, so we've already talked about exothermic, energy flows out. Endothermic, energy flows in. Part of chemistry that's concerned with how much energy flowed in, how much energy flowed out is calorimetry. 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 Of course, the most important extension of calorimetry to us is nutrition science, because in nutrition science, they want to find out how much energy is in those chemicals that make up the foods. How much energy is in the chemicals that make up the food. Nutrition science is all you really need to write down. Nutrition science is all you really need to write down. Hopefully, if you write down nutrition science, you'll realize, oh yeah, so this is the part of science that tells me how much energy I can get. And if you wonder why the American public is, on average, obese, that means we're overweight, grossly overweight, it's because we don't exercise, so we don't burn the calories, and we take in a lot of calories. So if you don't burn the calories, your body stores them as fat. Fat. So it accumulates it here in the tummy. I used to weigh 200, at my highest, 240 pounds. I weigh 185. So I lost 55 pounds. Okay? 55, 65 pounds. Okay? How? I just didn't give my body calories, carbohydrates. Okay, your body can only take so much protein and fat, and then it just gets rid of what it doesn't use. So if you're not giving your body carbohydrates like I used to, then it's not stored as fat. So I lost 65 pounds, limiting how many carbohydrates. One of the easiest ways you want to lose weight, it doesn't matter. Cut out your salt. Cut them out. Done. No fruit drinks, no soft drinks, all of that is just pure sugar. Your body, unless you are going to be like JK working out there in the heat, in the sun, that's just going to get stored as fat. So the one thing, it doesn't matter what diet you're on, the first thing they're going to ask you to do is cut out the drinks. Cut out the drinks. Unsweetened tea of any kind, water. That's it. And you're going to lose weight. Automatically, you're going to lose weight. You would not believe how many calories you get from the drinks that you drink. That's the fruit drinks and also the colas. Enormous. What device is used to measure the exact amount of energy that enters or leaves during a chemical reaction? It is called a calorimeter. A calorimeter. A calorimeter. And here is a calorimeter that costs several thousands of dollars. We don't have one of these. Let me explain to you what it is. The outside box is a highly insulated box. So if it's hot outside, it's going to be very hard for that heat to get inside. If it's cold outside, it's going to be very hard for the heat inside to get out. So this is going to be a very insulated outer box. The inner box, not so much. Heat can easily enter or come out of it. This is completely surrounded in water. This is a thermometer, and you're going to have two wires that go into that little cup that's inside. Typically, this is called a bomb. So this is a bomb calorimeter, as in bomb, okay? I don't know why it's called a bomb calorimeter or a bomb, but that's what it is. It's a bomb. Okay, so how are we going to find out that a Big Mac is 1,100 calories? Easy. They get McDonald's to provide for them a prototypical Big Mac. This is it. This is the Big Mac, which has the perfect amount of lettuce, the perfect amount of secret sauce, the perfect amount of everything, and the patties are cooked perfectly. This is perfect Big Mac. Then they take this beautiful Big Mac that you have never seen, because I doubt that we've ever eaten a perfect Big Mac, and they drop it into a blender, add a pitcher full of water, and then they blend the sucker until it becomes a soup. Okay? Now it's a soup. Everything has been just pounded into tiny little particles. They take this liquid and they put it in a special device called a dehydrator that basically sucks up all the water. So all the water that you added and all the water that's naturally in a Big Mac is sucked out, leaving you behind a powder. So a Big Mac, all that's left is a powder. They take a small amount of that powder. First of all, they weigh the whole powder. All of it is weighed. So they now know the total mass of a Big Mac. Then they take a small amount and they place it in this bomb right here. They attach the wires to it so that when the time comes, a spark will occur. And then they seal it up with a amount of water that they know, how much water there is in there. This is just a little stirring rod that keeps the water flowing. And when they're ready, they flip the switch. Electricity comes down here, catches the Big Mac powder on fire. Now, the Big Mac, in the presence of a lot of oxygen, they just fill up that bomb with oxygen. It just starts burning. The Big Mac starts burning, giving off energy to the water outside. All we need to know is how much water and what the water its change in temperature of the water, and we can figure out how much energy the Big Mac gave off. All right, that's the goal. Let me show you how to do that. We won't have a fancy calorimeter. We're going to have a coffee cup. Three things that you need to multiply in order to find out how much energy the Big Mac gave off. Q is equal to mass, change in temperature, specific heat. Mass, delta T, is change in temperature. You're going to need to write this down, change in temperature. the delta. That's a Greek letter delta. Just think triangle. Triangle T is the final temperature minus the initial temperature. The final temperature minus the initial temperature. It has to be in that order. Final minus initial. So M is for mass, triangle T is for final minus initial, and SH, or just the little s, is for specific heat. Now, what is specific heat? So let's use Amira, right? Amari, I'm sorry. Let's use you and you as examples. Okay, I'm just going to use your name because this is a silly example. It's not going to embarrass you. Okay, so Amari seems to me like one of these people that has a hair trigger anger mechanism. She is one of these people. Most of the time, she's just happy as can be. Every once in a while, if you make her mad, she gets very mad. So I can look at her and go, well, you look funny. I mean, I would say, I don't know how ugly you are from the nose down, but you're probably very ugly underneath that mask. And for those of you who are listening out there in YouTube land, this is taking place in September of 2020 in the middle of the pandemic. So she has a mask on. Okay, so I insult her and she goes ballistic. She throws the desk down. She's gesturing, using a finger to gesture at me to tell me how much she does not like the fact that I insulted her. Okay? And then she sits down like this and puts her arms, crosses her arms, and she goes like this. Obviously, she's very, very, very angry. By the end of the period, she's smiling again. She comes up to me, pats me on the back. Have a great weekend. I'm going, what in the world just happened? A few moments ago, she was giving me the bird, and now she is happy and wishing me to have a good weekend. Okay, does that pretty much, those of you who know Myra, does that pretty much describe her? She can get super mad really quickly, but then in the next few moments, she's your best friend again. Okay, if it isn't, we're going to make believe it is. All right, now let's compare that to you. Okay, Annabelle. Annabelle seems like the kind of person that, I insult her and she'll just go, whatever. I insult her again and she goes, whatever. An hour later of insulting her, every moment, you see a little eye twitch. She's getting a little irritated. 3 hours later, she gets up, tackles me to the ground, and starts to pound my head against the concrete. Then she gets up after, I'm dazed. She gets up and leaves the room. I don't see her for 2 weeks. Finally, she comes back and she's going, okay, I'm cool now. I'm good now. Where were you? I was cooling off. Is that what Annabelle's like? Takes a long time for her to get mad, but by golly, when she gets mad, she gets mad. And then it takes her a long time to cool down. Yes, makes sense? Do you know 2 people that are like that in your life? Somebody that gets mad really fast, and typically if they get mad really fast, they get over it real fast. And then the people that get mad very slowly typically take a long time to get over it. Okay? Who here in this class is number 1? You get mad fast and you get over it fast. I'm number 1. Okay? We have a low specific heat. Remember that. Low. Who here takes a long time to get mad and then it takes you a long time to get over it? Okay. You have a very high specific heat. Very high specific heat. Okay? We'll get to it. Why do we care only about what happens to water? What happens is the opposite of what happens to the reaction. If water warms up, what did the reaction do to the water? Warmed it up. if water cools down, what did the reaction do to the water? It took its energy away. So whatever happens to the water, the opposite is going to happen to the reaction. Notice this, a positive Q. Q is energy. If the water absorbs energy, the reaction must have given off the energy. What is specific heat? The amount of insults, not insults, heat energy. The amount of insults, heat energy required to get somebody mad by 1 degree Celsius, to get somebody that weighs only 1 gram mad by 1 degree Celsius. How much energy is required to get 1 little gram of a substance to go up by 1 degree Celsius? Every substance has its own unique specific heat, has its own unique specific heat. The specific heat of water is 4.18 joules per gram C. The specific heat of water is 4.18 joules per gram C. On the back of your periodic table, this is going to be the first thing that I ask you to write down on your periodic table. Down here at the bottom, put this information. You should see a space down in the bottom on the back of the periodic table. On the back of the periodic table, make sure you put down the periodic table that should be out. Make sure you put down that little piece of information. Now, you may go 4.18. Wow, that's a small number. No! That's a very big number. That's a very big number. Most specific heats are under 1. Most specific heats are under 1. All right, so here we go. Miss that, then you'll have to watch it on video. This one right here, that's Annabelle. This one right here, that's Amara. Okay? Watch what happens when I heat. Notice that their masses are the same. They are exactly the same. One is water, one is steel. I'm going to warm them up by insulting them. You're ugly! Ah! What's the temperature of the water? 0, no change. What's the temperature of the iron? Went from 0 to 114. That person is already very angry. I insult them again. Water goes, what? Did you say something to me? Iron is going, ah, I'm going to kill you. I insult them again. Water is going, what? Iron is now pounding my face with their fist. I insult them again. Water's going, did you say something nice? Or did you say something mean to me? And iron has now, hair's on fire. They are running out the door. They can't take it anymore. Check it out. The amount of abuse that it took for water to not change 1 degree. Iron changed from 0 to 455. Why? Because iron has a low specific heat and water has a high specific heat. So if something warms up very quickly and cools down very quickly, low. If it warms up very slowly and cools down very slowly, high. Plastic. What do you guys think? Raise your hand. High or low? High or low? High or low? Come on, it's a 50-50. Natalie. Yes. Okay. Why high? Well, I've got a lot of utensils at home used for grilling. Okay. The handles are either plastic or wood. Why would it not be smart for there not to be a handle, for it just to be pure metal all the way to the top? Yeah. Okay. So the handles on things being plastic or wood makes it so that it doesn't heat up very quickly and we can handle it. We can use it as a handle. So you are correct. How about a copper pot? Has anyone ever used a copper pot or a pan? Very, very expensive. You know why? Because it's super good. Okay, only rich people can afford copper pots. Why? Why do people want to use copper pots? Somebody besides you. Come on, another one. High or low? Come on, this is easy. Morgan. Low. Very, very low. So you're cooking with a copper pot, bam, heats up very quickly. You want water to boil, bam, within 2 minutes it's boiling. Steel pots or pans, high or low? Raise your hand. Yes, low. So if you can't afford copper, maybe you can afford steel. Not as good as copper. Wood, high or low? I already gave this away. On a bet. High. Oil. Let me give you a clue. When I was your age, I used to work at McDonald's. Thankfully, I wasn't in the first crew that went in. The first people that went in at 4 a.m., the first thing they did was turn on the oil. So that by the time us grunts, us cooks came in at 6, we could start frying things. Raise your hand, high or low? Yes, high, yeah. Because oil has such a high specific heat, it took a while for the oil to get hot enough to cook with. Alcohol. Yes, very low. That's why alcohol evaporates very quickly. That's why it feels cool to your skin, because it absorbs your energy, gets super hot, and leaves. Perfume. Let me help you with this one. Perfume is mostly made up of alcohol. Luke, low. And glass, like the glass windows, high or low? Josh, high. How do you know? Well, I mean, feel the glass. Does it get super, super hot? Does it get super, super cold? The frame will, but not the glass. Some examples. Notice all these metals are super low. Depending on whether it's solid, liquid, or gas, it can change. All right, here we go. Calculators. Make sure that they are out and you are calculating. The equation that we will use is Q is equal to M times delta T times specific heat, where delta T is final temperature minus initial temperature. Determine energy. That's Q. That means they've told us everything else. Grams is what? Say it out loud. What is grams? Mass. Do we know what temperature it finally ended up on? From, to, do we know what temperature it began with? Do we know the specific heat of water? I didn't tell you the specific heat of water. But if you don't know the specific heat of water, you can't solve for Q. So the question you need to ask yourself is, could the specific heat of water be somewhere that I should be able to get it from? And the answer is back of your periodic table. What does it say? Say it out loud. 4.18 units divided by, it takes 4.18 joules to take 1 gram and make it go up by 1 degree C. Now, the reason why keeping all those units is important is because you need to be able to cross them out. So what's the only unit that's left? All right. You, sir, do you have an answer for me? I see you with your calculator in your hand. That's good. What's the answer? What? Can I get a confirmation on that? 525. All right. Units? Very good. And positive or negative? Okay. For Q, you have to say positive or negative. It's the only thing in chemistry that you will have to say positive or negative. Very good. Any questions? Yes. 46 minus 29. What is it? Go. 46 minus 29 is 17, isn't it? Times 7.4 times 4.18. If Q is negative, it's exothermic. Energy is going out. If Q is positive, energy is going in. Okay, we're running out of time, so I'm just going to do this for you without your help. Energy tells me it's going to be the Q equation. Ten grams is mass. 246 means that the final temperature is 46. From 25 means that that's where it started from. Do I use 4.18? No. The specific heat is given to me. It's 0.45. Grams cross out, Celsius crosses out. The answer is going to be in joules. I think it's going to be a positive answer. I need somebody to very quickly calculate. Anybody? Josh. Probably need to have a decimal place. No, you're right, 94 joules. Can I get a confirmation on that? Excellent. Any questions on that one? Just like the first one. Now, this is algebra, isn't it? Just solving for x. So you can imagine I can throw in a little curve like this. Q is equal to mass times final minus initial times specific heat. A 1.6 grams, that's mass, has an appearance of gold, so we don't know whether it's gold or not, and requires 5.8 joules. In the last two questions, we've solved 4 joules. Now they're telling us that it is joules. So requires positive 5.8 joules. The temperature changes from, it ends up at 41, it starts at 23. Now, this is confusing. They're giving us specific heat, but then the only thing that's left to solve for is specific heat. Well, we don't know whether this is gold or not. So if we solve for specific heat and it ends up being 0.13, then it's gold. Then it's gold. So subtract those two numbers, multiply by 1.6, and then take that number and divide it into positive 5.8. Go. None of the units cross out, so it's going to be joules per gram C. If the number is not under 1, you've done something wrong. 41 minus 23 is 18 times 1.6, and divide that number into 5.8. Who has it? Okay, if the number is not under 1, you've done something wrong. I believe.
"9:46 on this Saturday morning. It's time for Imagine It, and I'm donning some really amazing wear here. Carl Nelson joins us. Hi.
We got your fire retardant lab coat on, just in case. Mine is as well. We're going to talk about calories today.
All right.
Calories in food. Calories are not bad. They're just a measure of energy.
Okay.
And so I brought with me two different kinds of food. If you can grab a handful of toasted oats and just toss it in this little porcelain bowl, we kind of got one end of the spectrum of food there.
Okay.
Got some cheese puffs here. Oh, load that thing up.
Oh, load it up. All
We're
right.
going to load it up. What we're going to do is we're going to measure how many calories there are in each of these samples of food. Now, if we were food scientists, nutritionists, we would do this in a very careful and exacting way. We're going to do it really sort of down and dirty today.
No problem.
We're going
just in the studio, right? No big deal.
Exactly. What we're going to do is we're going to burn these samples, and we're going to measure or observe the flame that comes off. All right? Now, you could do that just by toasting them with the torch.
Okay.
But that's not going to be good enough. We need an excess of oxygen to get them to really combust well. And to do that, I brought with me, or I actually manufactured here, a little liquid oxygen. This blue liquid is liquid oxygen. It's about 2 balloons.
9:46 on this Saturday morning. It's time for Imagine It, and I'm donning some really amazing wear here. Carl Nelson joins us. Hi.
We got your fire retardant lab coat on, just in case. Mine is as well. We're going to talk about calories today.
All right.
Calories in food. Calories are not bad. They're just a measure of energy.
Okay.
And so I brought with me two different kinds of food. If you can grab a handful of toasted oats and just toss it in this little porcelain bowl, we kind of got one end of the spectrum of food there.
Okay.
Got some cheese puffs here. Oh, load that thing up.
Oh, load it up. All right.
We're going to load it up. What we're going to do is we're going to measure how many calories there are in each of these samples of food. Now, if we were food scientists, nutritionists, we would do this in a very careful and exacting way. We're going to do it really sort of down and dirty today.
No problem.
We're going
just in the studio, right? No big deal.
Exactly. What we're going to do is we're going to burn these samples, and we're going to measure or observe the flame that comes off. All right? Now, you could do that just by toasting them with the torch.
Okay.
But that's not going to be good enough. We need an excess of oxygen to get them to really combust well. And to do that, I brought with me, or I actually manufactured here, a little liquid oxygen. This blue liquid is liquid oxygen. It's about 2 balloons worth of oxygen. Far more oxygen than we need to combust this stuff. So here's the deal. I'm going to give you the torch.
Okay.
I know you're excited about
All
that.
right.
I'm going to pour the oxygen on the cereal. You're going to hit it with the torch, and then you should probably block your vision. Okay?
All right. This is going to be the end of the road for me, folks.
Go ahead and light that thing up. Don't bring it over quite yet. Get ready. All right. Bring it over and hit them. Hit it and hold it there. All right.
Did I do it too soon?
No, that was great. So now you're getting a sense of how much energy there are in those toasted oats. They're really toasted at this point, right? Very, still going. Very bright flame.
Yeah.
All right. Let's try it with the cheese puffs.
Okay. Now, do I need to hold it on there longer or a little bit less?
No, you did actually really well.
Okay.
That was pretty good. And, we don't want the smoke alarm to go off, so we'll cover that up. All right, so go ahead and light up your torch again.
All right.
So this is the comparison. This is the cheese puffs. Let me get the oxygen in there. Go ahead and hit them. Hold it there for a second. Okay, pull back.
Oh, wow.
Okay, see, that's why I brought the fire extinguisher as well.
Sure.
Incredible amount of energy coming off those cheese puffs.
You can feel the heat from that.
You can feel it. You can see it. I'm going to cover some of these up here.
No big deal, Carl.
All right. There's a lot of smoke here now. But I mean,
we have insurance.
The idea, excellent. I do too. The idea here is that there's energy in the calories.
Okay.
And I'm not suggesting you eat all cheese puffs all day, but it's just a measure of energy, okay? So the toasted oats are probably a better choice if you're going to consume just one of these two items.
Sure.
But they both have tons of energy in terms of calories.
And that's why the puffs burn longer, because they have more calories?
The puffs actually have a little bit of oil in them, so that helps them burn a little bit more, and they do have a few more calories. We kind of just did it really quickly here. We threw a handful
Not too
in.
scientific.
About 100 calories or so. But just calories, measure of energy.
Interesting. And